I'm looking at a machine learning problem where we're using scikit-learn's partialdependence to understand how two features, feature underscore A, continuous, and feature underscore B, categorical with levels, low, medium, high, affect a target variable. The partial dependence plot for feature underscore A shows a clear positive linear relationship, but the plot for feature underscore B is flat. This means that feature underscore A strongly influences the predictions, but feature underscore B doesn't seem to have much of an impact. The partial dependence plot, PDP, for feature underscore A shows a straight upward sloping line. This tells me that as feature underscore A increases, the model predicts a higher value for the target variable. That's a strong positive relationship. In contrast, the PDP for feature underscore B is flat. This means the model's prediction doesn't change much regardless of whether feature underscore B is low, medium, or high. This suggests feature underscore B has a weak or no effect on the model's predictions. We're trying to interpret partial dependence plots. PDPs show how much a feature influences the model's predictions after considering the effects of other features. A flat PDP for a feature means the model isn't very sensitive to it. The key is to carefully examine both PDPs. I will analyze the slope of the line in the feature underscore A plot and whether the feature underscore B plot exhibits any significant variation. This lets me gauge which feature is more important to the model. I see a question about interpreting partial dependence plots, PDPs, from scikit-learn, a popular machine learning library in Python. We're given that feature underscore A shows a positive linear relationship with the target variable in its PDP, while feature underscore B shows a flat PDP. This means that feature underscore A strongly influences the prediction, but feature underscore B shows little to no effect. The partial dependence plot, PDP, for feature underscore A shows a clear positive linear relationship. This means as feature underscore A increases, the predicted value of the target variable also increases in a straight line. This indicates a strong positive correlation. The PDP for feature underscore B is flat, indicating that the average prediction of the target variable is roughly the same across all three levels, low, medium, high. In other words, the model doesn't seem to be using feature underscore B to make predictions. This is the key observation. I agree. The PDP clearly shows a strong relationship between feature underscore A and the target variable, while feature underscore B shows almost no relationship, leading me to believe feature underscore A is more important for prediction. The positive linear relationship in the PDP for feature underscore A makes a linear model plausible, but it is not definitive. Other models can also display linear relationships in their marginal effects, such as some tree-based models under certain conditions. Therefore, while possible, I can't say for certain it's a linear model. I'm analyzing partial dependence plots, PDPs, to understand how features affect a model's predictions. PDPs show the average effect of one feature on the model's prediction, keeping other features constant. This helps us understand feature importance and identify possible relationships. This technique is very valuable in interpreting black box models. The flat PDP for feature underscore B suggests it's not a strong predictor. However, it doesn't necessarily mean the model is completely ignoring it. The model might still be using feature underscore B in complex interactions with other features, which won't be captured by the marginal effect in the PDP. It could also be that its effects are very subtle and not easy to see in a simple PDP. While possible, we can't conclude there is significant interaction between feature underscore A and feature underscore B, only based on the information provided. A flat PDP for feature underscore B doesn't rule out a strong interaction effect. Further analysis is needed to determine whether such interaction exists. I'm going to explain how we can determine the relationship between features and a target variable using partial dependence plots, PDPs. PDPs show how models' predictions change as one feature varies, averaging out the effects of other features. This helps us understand each feature's individual impact on predictions. We're given a scenario where we use scikit-learn's _partial_dependence to analyze a model's predictions based on two features. Feature _A, continuous, and feature _B, categorical with levels, low, medium, high. The PDP for feature _A shows a positive linear trend, while the PDP for feature _B is essentially flat. My goal is to understand what this tells us about the model and the importance of these two features. Let's dive in. I see a clear positive relationship in the PDP for feature _A, indicating that as feature _A increases, the model's prediction increases significantly. In contrast, the flat PDP for feature _B shows minimal change in prediction across its different categories. Therefore, I conclude that feature _A has a much stronger influence on the model's predictions than feature _B. The linear relationship shown in feature _A's PDP is consistent with a linear model, where the relationship between a feature and target is a straight line. However, it's important to note that this is not definitive proof. Other models can also exhibit linear trends in their PDPs. So, I'm saying it's plausible, but not necessarily certain. I'm using a powerful tool from scikit-learn called _partial_dependence to analyze my model. I'm interested in uncovering how feature _A, a continuous variable, and feature _B, a categorical variable with 3 levels, relate to the target variable. I'm going to analyze partial dependence plots, PDPs. PDPs show how machine learning models' predictions change when you change one feature while keeping all other features constant. It's like looking at the relationship between one ingredient and the final taste of a dish, regardless of the other ingredients. We'll focus on interpreting the plots to understand how important different features are. The PDP for feature A shows a straight upward sloping line. This means that as feature A increases, the model predicts a higher target variable. It's a pretty clear and direct relationship. More A, more target. Think of it as a simple recipe. The more of ingredient A you add, the spicier the dish gets. The PDP for feature B is flat, like a pancake. This means that changing the value of feature B doesn't really change the model's prediction. It's like adding ingredient B. The taste remains the same, regardless of whether you add a little or a lot. That doesn't necessarily mean the model ignores feature B completely, but its impact on the final prediction is minimal. It could be masked by other features or interactions. We are given a machine learning model and its partial dependence plots for two features, feature _A and feature _B. I'm analyzing the plots to determine the relationship between the features and the target variable, as well as making inferences about the model itself. It's like a detective story where the plots are our clues. Because the PDP for feature A shows a linear relationship, it is plausible that the model itself is linear. But remember, this is not a guaranteed conclusion. Other more complex models can also exhibit linear relationships in their marginal effects. It's a possibility, but I need more evidence to be certain. It's like saying, if the shadow is a straight line, the object might be a stick, but it could also be a straight line object. Looking at the PDPs, it's clear that feature _A has a much stronger effect on the target variable than feature _B. Feature _A exhibits a strong positive linear relationship, meaning a clear increase in prediction as the feature increases. Feature _B has a flat PDP, showing little to no impact on the prediction. Therefore, feature _A is clearly a stronger predictor in this model. This is a solid conclusion based on the data. It's like comparing a powerful engine to a tiny spark plug. The engine clearly has more predictive power. I'm analyzing partial dependence plots, which are visual tools showing how a single feature influences predictions in a machine learning model, after accounting for other features. Think of it like this. I isolate one feature and see how it impacts the model's output, ignoring other factors for a moment. I'm tackling a question about interpreting partial dependence plots, focusing on what they tell us about features' importance and a model's behavior. I analyze the relationships between features and predictions revealed by partial dependence plots to determine which features are important predictors. I will investigate whether features have strong or weak effects based on the plot's shapes. The partial dependence plot for feature A shows a positive linear relationship with the target variable. That is, as feature A increases, the model predicts a higher value for the target. This signals feature A's strong predictive power. The partial dependence plot for feature B shows a flat line. This tells me that changes in feature B don't significantly influence the model's predictions. This does not imply feature B is completely useless, only that its direct marginal effect is weak. A flat partial dependence plot for feature B doesn't rule out an interaction with feature A. It's possible that feature B only matters in certain ranges of feature A. More analysis is needed to confirm this. It's a tricky one. Because the PDP for feature A shows a linear relationship, it suggests the model might be linear, but it's not definitive proof. Other models can produce linear partial dependence plots. While the flat plot suggests that feature B's direct effect is weak, it doesn't mean the model completely ignores it. Feature B could still be indirectly influencing the predictions. PDPs only give us the marginal effect. There might be hidden interactions. I'm analyzing partial dependence plots, PDPs, to understand how features influence a model's predictions. PDPs show the relationship between a feature and the target variable, averaging out the effects of other features. It's like looking at the effect of one ingredient on a recipe's taste, while ignoring all the others. I'm going to explore how to interpret partial dependence plots and use that knowledge to answer questions about a model's behavior. This is crucial for understanding feature importance. I have a machine learning model and I'm using PDPs to investigate the relationship between the target variable and two features. Feature _A, continuous, and feature _B, categorical with 3 levels: low, medium, high. From the plots, I see that feature _A has a clear positive linear relationship with the target variable. As feature _A increases, so does the prediction. However, feature _B shows almost no change in the prediction across its 3 levels. The plot is essentially flat. I'm given some statements about the model and the features, and I need to determine which ones are likely to be true based on my PDP analysis. This requires a good understanding of PDPs and feature importance. This might seem plausible given the flat PDP for feature _B, but it's not conclusive. The model might still use feature _B in complex ways, such as interactions with other features. The positive linear relationship for feature _A and the flat line for feature _B strongly suggests that feature _A is more influential in shaping the model's predictions. This is possible, but the flat PDP for feature _B alone doesn't confirm it. We would need further analysis to verify the existence of a significant interaction effect. The linear relationship in feature _A's PDP hints at a linear model, but it's not definitive proof. Other models can also exhibit linear relationships in their marginal effects as shown by PDPs. I see, you're using SCIKITLEARNSPARTIAL_DEPENDENCE function to explore how two features, a continuous one, feature _A, and a categorical one, feature _B, influence your prediction. The plot for feature _A shows a clear upward trend, meaning higher feature _A values are associated with higher predictions. But feature _B shows a flat line across all its categories, low, medium, high, suggesting it barely affects the predictions. The question asks you to determine which statements are most likely true, given this information. Let's analyze each statement carefully. This statement is highly probable. A strong positive linear relationship in feature _A's partial dependence plot strongly suggests that it's an important predictor. On the other hand, the flat plot for feature _B tells me feature _B barely influences predictions. This is a plausible option, but not certain. The linear relationship in feature _A's plot could be Consistent with a linear model. Because linear models are known for direct feature relationships. However, other models, even complex nonlinear ones, can also have linear marginal effects, visible in partial dependence plots, so I'm not able to say this definitively. We are only observing marginal effects here. This possibility is open. A flat partial dependence plot for feature underscore B doesn't rule out interaction effects. The effect might be small in the marginal plot, but it could still exist when we consider the interaction with feature underscore A. A conditional effect of feature underscore B on prediction given a specific value of feature underscore A could exist, and the partial dependence plot might not display this clearly. This statement is unlikely. Although feature underscore B shows a weak marginal effect, the model might still use it. Remember that interactions might exist and are not captured by this marginal effect in the plot. This is the title of the analysis. Partial dependence plots are a valuable tool for understanding how features impact predictions in machine learning models. They show the average predictive value across a specified feature, considering the marginal effect, and are used for assessing the predictive power of specific features.